not be a lecture next month because of the open house, which we would encourage you to attend. That is May 15th and 16th, 9 to 5 both days. No reservations or charge for admission or parking. Okay? All right, thanks. All right, let's jump in, shall we? The Wide Field Infrared Survey Explorer, WISE, launched December 14th, 2009, and a month later began surveying the sky in 4 infrared wavelengths, ranging from 4 to 30 times redder than our eyes can see, and it continues the JPL-Caltech tradition, of mapping the infrared sky. Its megapixel infrared detector arrays make the WISE survey hundreds to hundreds of thousands of times more sensitive than previous all-sky surveys, which used only dozens of pixels. The satellite is observing everything in the universe, from near-Earth asteroids to dusty, cataclysmically forming galaxies over 10 billion light-years away, and is expected to discover hundreds to perhaps thousands of new objects. Tonight's guest always wanted to be an astronomer, and often wondered how anyone could not want to explore the universe. He majored in physics and astronomy at the University of Pennsylvania, then spent a year at Cambridge University, and then completed his PhD on galaxy evolution at the University of Arizona. In 1987, he began working on Spitzer, or the Space Infrared Telescope Facility, as it was called then, and then came to JPL in 1990 when project management was transferred there. His work on finding galaxy clusters with Spitzer earned him JPL's Ed Stone Award for Outstanding Publication, and he was awarded NASA's Exceptional Scientific Achievement Medal in 2009. Back in 1994, he and Professor Ned Wright of UCLA began developing the concept for the Wide Field Infrared Survey Explorer. Today, when our guest isn't playing the French horn in the Caltech Occidental Symphony, he and Dr. Wright continue to share responsibility for WISE as it explores the infrared universe, with Wright serving as the principal investigator and tonight's guest as the project scientist. Please join me in welcoming tonight's said guest and WISE project scientist, Dr. Peter Eisenhardt.
Thank you, Mark. See, can everybody hear me? Well, good evening. It's a real pleasure and an honor to be asked to give the von Kármán lecture in von Kármán Auditorium. It's really quite a thrill. I've been at JPL for just about 20 years, and a little over half that time has been spent trying to make WISE happen. So it's tremendously exciting to be more than halfway through the sky survey, as I'll show you a little later, and to have some spectacular imagery to show you. I want to start with a very, very quick reminder of what WISE is, and then I'm going to do a little bit of a tutorial about what infrared is, because WISE is the Wide Field Infrared Survey Explorer. So as Mark mentioned, it's an all-sky survey in 4 infrared bands, and they're listed here. Let's see if I can make the laser pointer work. There we go. So 3.4, 4.6, 12, and 22 microns, and those are wavelengths that are roughly 5 to 30 times redder than what we see with our eyes. And I'll say a little bit more about that, what that means in a minute. And the sensitivity is hundreds of thousands of times better than previous infrared all-sky surveys. And so that's really a huge advance, and it's made possible by these megapixel infrared detector arrays versus the previous all-sky surveys in the infrared were done with dozens, or in fact just a few pixels in the case of a couple of our wavelengths. And what we'll be delivering when we're done with our survey is over 1 million calibrated images and catalogs of hundreds of millions of objects in these 4 infrared bands. So I think Mark said we would expect to discover hundreds, if not thousands, of objects. We actually expect to find millions, maybe hundreds of millions of new objects. So a lot of new stuff coming out of WISE. But before I tell you more about WISE, I want to tell you a little bit more about infrared. Infrared was actually discovered by Sir William Herschel in 1800. He was trying to measure the temperature of sunlight, and he was using thermometers to do it. So what he did is he took a prism and made the sun spread out into the familiar colors of the rainbow, from indigo through red. And he put thermometers at various places along the spectrum of the rainbow there, and you can see what's happening there. And he took the temperature of those different wavelengths from blue to red. And then he put a control thermometer where there wasn't any light that he could see out beyond the red. And to his surprise, what he noticed was that thermometer was also warming up when he spread out the spectrum here. And so he realized there was energy falling at wavelengths beyond the red here, longer wavelengths than what our eyes see. And that's what he named infrared. And so that's why we call it infrared, because Herschel called it that 200 years ago, 210 years ago. Here's a little bit more information on the whole electromagnetic spectrum. Now, our eyes respond to really quite a small range of electromagnetic radiation that we call visible light. And those wavelengths measured in micrometers or microns, which is a micron is a millionth of a meter or a thousandth of a millimeter. In microns, those wavelengths range from about 4/10 of a micron to 7/10 of a micron. So if the wavelength of the light is a little less than half a micron, and a micron is about the size of a bacterium if you want a sort of a scale. If it's the wavelength is about 4/10 of a micron, we call that blue, and if it's shorter than that, we don't see it anymore. It moves into the part of the spectrum that we call ultraviolet. And then the red wavelengths that we can see out to about 7/10 of a micron. And if it's longer than that, then we're in the infrared. And this is where WISE operates. There are longer wavelengths out in the microwave and radio, and there are shorter wavelengths in the X-ray and gamma ray, but I'm going to be focusing on the infrared. Now, to give you a little better idea of what infrared really is, I'm going to go to the infrared camera here. So if we could switch to the infrared camera, give you a sense of what the auditorium looks like in the infrared. Or if that doesn't work, I can show you some slides. But can we switch to the infrared camera? There we go. Okay, so there you all are in the infrared. So what you're looking at is basically not radiation that's reflected by these lights around the room, but radiation that you're emitting. And I should give everybody a chance to wave at the camera here, I guess. And you'll notice that your glasses, when you're wearing glasses, are dark, and your faces are generally quite light. Your clothes are darker, and that's because those parts of you are warmer. And so you're putting out more radiation actually at all wavelengths, but particularly in the infrared. Every object that has a temperature puts out radiation across the electromagnetic spectrum. The hotter it is, the shorter the wavelength where that radiation comes out. And so the sun is pretty hot. It's about 11,000 degrees Fahrenheit. And it puts out most of its light in that 4/10 to 7/10 of a micron range that we call visible light. And there's a good reason for that. Our eyes adapted to take advantage of the sunlight. Things that are cooler than the sun, such as the people in this room, emit primarily at longer wavelengths. And so if you're twice as cool as the sun, you're going to emit at twice as long a wavelength. But in fact, none of us are 5,000 degrees Fahrenheit or 3,000 degrees centigrade. We're more like 100 degrees Fahrenheit or about 30 degrees centigrade. And that's a temperature that's about 20 times colder than the sun. And that means the wavelengths that we put out, most of our radiation, are about 20 times longer than that half micron kind of light that the sun puts out most of. And so instead of being half a micron peak light, most of our light is coming out at about 10 microns. So what you're looking at here is out in the several micron to 10 micron range. Okay, and that's very sensitive to kind of room temperature objects. Now let's look at some objects over here. So I have a couple of props that I brought along. And let's see if people can kind of guess what's going on here. Let's see if we can. Okay, so you see my travel mug there. That's glowing very, very brightly, and that's because it's hot, right? It's actually tea, but close enough. Okay, and then this guy here says ice pack, and indeed, it's very, very dark. Okay. Now, you'll actually notice if I put my hand on this for a while, you can see a little bit of a glow, so we can pick up that kind of signature. So this gives you a basic idea what infrared is doing. It's picking up variations in temperature at temperatures that are around room temperature and colder, and a little bit warmer as well. And so that's what WISE is really designed to do best, is pick up objects that are cool compared to the stars that we're more familiar with. Another good thing about infrared, besides picking up this sort of hidden cool universe, is that it can see through things that visible light can't. So if I go back over here to our, focus this up a little bit for you. If I go back over here to the mug, now if I put the bag over this, you won't be able to see the mug very well. But it makes almost no difference at all to the infrared view. Infrared penetrates through things that visible light can't, including dust. And there's lots and lots of dust in the universe. And so infrared is going to let us peer through dusty regions, which are very interesting regions in the universe, and see what's going on there in a way that's not possible with visible light. Okay, let's go back to the slideshow now. I'll use the camera again a little bit later in the talk, but I wanted to give you a sense of what infrared was all about. So if we could, great, okay. So now I'm showing you a picture of the entire sky at 3 different wavelengths. Visible light that we see with our eyes, and the Milky Way, that is our own galaxy, is running across the center of this image. Let's see if I can make the pointer work again. Here we go. So the plane of our galaxy, the Milky Way, is running across the center, and the center of our galaxy is right dead center there. And you can see it's actually kind of murky. It's actually very dusty. There's lots and lots of dust between us and the center of the Milky Way. In fact, we can only see a few % of the way to the center of our galaxy. The dust blocks our visible light view from seeing further than that. Now, if we go out into the infrared wavelengths, the shorter infrared wavelengths, this is around a ½ micron. Now we're going to go out to 2 microns, which is about the longest infrared that you can do from the ground. This is the view of the whole sky that we see. And now the whole galaxy is very, very clear, and the center of the galaxy is very, very clear, although you can still see some evidence for dust. So even at these wavelengths, the dust is still blocking our view a bit. If we go, and what we're seeing here is the stars that make up the Milky Way, and there's lots and lots of them in the middle. You can also see some stars from nearby satellite galaxies called the Magellanic Clouds down here. If we go now to longer wavelengths, now we're talking about 20, 50 micron wavelengths that were surveyed by the infrared astronomical satellite IRAS in 1983. This is the view that we see of the sky. And now actually this bunch of old stars here that's in the center of our galaxy is largely invisible. What we're seeing now is and we're also not seeing any of this obscuration due to dust. We're actually seeing the dust itself glow. These are wavelengths like 10, 20 microns, similar to what I was showing you with the camera, where room temperature and a bit colder than room temperature is actually glowing very brightly. And so now we're seeing the dust, rather than blocking light, the dust is warm and it's glowing in the infrared. And we're seeing warm dust all across the Milky Way that's actually being heated up by new stars. There's typically lots of dust associated with young stars forming, and actually with stars dying as well. And we're tracing where the stars are forming and dying, and you can see it's actually a very, very thin line right across the sky there in our Milky Way. So that's the kind of a view that we get with WISE is more like this here in the infrared. Okay. Now, I showed you that picture a moment ago that was taken from the ground at 2 microns. That was the one where you could see the Milky Way and the old stars very well. So why should we bother going to space? Well, if we want to go to longer wavelengths than that 2 micron range, what we find is the glow from room temperature objects, people, the ground, the air, the telescope, starts shooting up dramatically. This is a plot of how bright the background is, the air, the people, the ground, versus wavelength. And you can see when you go to longer wavelengths than 2 microns, it starts zooming up here. Every one of these tick marks is another factor of 10. So when we go from -5 up on tick mark, we've gone 10 times brighter background, 100 times, 1,000 times, 10,000 times, 100,000 times. By the time we get out to sort of these wavelengths where room temperature objects like people and cool dust and warm dust that's around forming stars is emitting, we're talking about over 1 million times more background. So what that means is it's very, very hard to see through all that glare that's in front of us and see the faint objects that are farther away that we want to study. And so it's been said that doing ground-based infrared astronomy is like observing stars in broad daylight with a telescope that's made out of fluorescent light bulbs. It's, you can do it, but it's hard. And that's really true when we get out to these 5, 10, 20 micron wavelengths. And so our telescope on WISE, which is not very big, it's only about this big in diameter, is the equivalent of thousands of the largest telescopes that we have on the ground because of that factor of over 1 million improvement in the brightness. There's one other thing that we have to do to take advantage of this. Space itself is much, much darker because we don't have all this warm stuff glowing around. But we also have a telescope, and that has to be cold. And so it's very important to keep that telescope cold. And so we have a supply of frozen hydrogen that we carry along with our telescope. And I'll say a little bit more about that in a minute. Okay, so here is WISE again on a slide. And what you can see here is WISE at Vandenberg Air Force Base getting ready to launch, a picture of launch itself in our first picture. And I'll show you all these again. But we initially proposed WISE a long time ago, back in 1998, and we almost got picked, had to come back for a second try because we came in as the first runner-up, but they didn't quite pick us. We trimmed back a little bit and tightened up our concept, and in 2001 we got picked, and then finally last December, on December 14th, as Mark said, we launched. Just before New Year's Eve, we released the cover that keeps the telescope in a vacuum. When we're on the ground, we're cooling it with this frozen hydrogen to about minus 440 degrees Fahrenheit, really, really cold. And if you were not having that in a vacuum and sealed off, the air that's around would freeze onto the telescope. Instead of having a telescope, you'd have a popsicle, which is not really much good. So we kept it covered and in a vacuum until about 2 weeks after we launched, just before New Year's, as I said. We ejected the cover. And then a few days later, we took our first pictures and released them, and I'll show you that again in a second, and then started the survey for real a month after launch on January 14th. About a month after that, we released our first pictures from our survey, and I'll show you those. And we're covering the sky at a very steady clip here. We're more than halfway done covering the sky, and by July, we'll have covered the entire sky. But we're going to keep going as long as that supply of frozen hydrogen will let us. The frozen hydrogen supply is expected to last until October, so we'll go 1.5 times around the sky, maybe a little bit longer if we're lucky, and that will be very, very useful. 6 months after that, cryogen runs out. We're going to release our first major chunk of data, preliminary data release, and then about a year after that, a little less than a year after that, in March of 2012, will be our final data release. Okay, so here's how WISE works. We launched, as I said, December 14th, into an orbit over the Earth's poles here. And what WISE does all the time, this is all it does, is map the sky. It scans a strip over the orbit. And so it's always pointing away from the Earth, scanning around. And normally that would smear images, but we have this scan mirror here, which I think you can see is scanning back and forth. And so what that does is it scans at exactly, while the satellite is scanning overhead like this, the scan mirror is scanning in the opposite direction. So those two motions compensate. And so what that means is we get a freeze frame image, which you can see sort of illustrated here. It's about 3/4 of a degree, or about 1.5 times the diameter of the moon on the sky. So we get one of these images with about a 10-second exposure time. And then after that 10 seconds, the scan mirror, which let me start that up again, you'll see it's scanning along there, and then it snaps back. And the reason it snaps back is that the satellite keeps going and going and going like this. The scan mirror is going like this, but it can only go so far. And so then it has to catch up with where the satellite is now. And so we take another picture 11 seconds later, and has just a little bit of an overlap with the first picture, and that's shown in orange here. And then we take another picture 11 seconds later, and another one. And so we take an image all the way around there, as you can see. And that's how we get a ring of images all the way around the sky. Okay? But that's only the beginning. On the next time around the orbit is actually shifted a little bit. The orbit is designed so that it always stays pointing us at right angles to the sun. And so it shifts just a little bit. On the next orbit, you can see that we get a strip of images that shifted a little bit, about 10%. And so we get, where we had 2 pictures just in this little strip before, now we have 2 pictures where these 2 orbits overlap, and then 3 pictures in some places. And that orbit keeps shifting a little bit, and eventually it will shift all the way around the sky. And in 6 months, as the Earth goes from one side of the sky to the other, that orbit keeps up with the Earth, always pointing at right angles to the sun, and so it sweeps all the way around the sky. And so what you see there is our coverage all the way around the sky, and the least covered part, which is across the middle there, we're getting at least 8 observations of any point in the sky. So we get lots and lots of redundancy to check how we're doing. Okay, so just wanted to spend a little time on that because it's quite important to understand how the basic survey works. Okay, well, it takes more than the scan mirror and the satellite to make WISE work. It takes a lot of other components. It takes a rocket for sure. I'll show you some more pictures of the rocket. This is a Delta II rocket that's done for us by the United Launch Alliance and managed by the Kennedy Space Center. It takes, of course, the satellite, which has 2 major pieces. This upper part, which has the frozen hydrogen and the telescope in it, and that was made by a company called Space Dynamics Lab in Utah. And the electronics and communications and power systems, that was done by a company called Ball Aerospace in Boulder, Colorado. And we're taking all these images every 11 seconds. We have to get them to the ground somehow. The way we do that is we transmit them to another satellite called the TDRS satellites. And these are satellites that are actually higher in orbit than WISE is. They're orbiting in what's called geosynchronous orbit. So 4 times a day, we orient WISE so that it can transmit those images to the TDRS satellite at 100 megabits per second, and then TDRS sends them to White Sands, New Mexico. From White Sands, they're sent to the Science Data Processing Center, which is at Caltech. And the housekeeping and health checking information is sent over to JPL, to Building 264, which is across the mall there, which is where we operate WISE from. And also we need survey plan to be commanded back up to the satellite, and that comes from our principal investigator, Professor Ned Wright at UCLA. So the Science Data Center here over at Caltech is, they're doing a lot of work. They're dealing with these images coming in every 11 seconds, and they're turning them from things that look kind of like this to ones that remove all these artifacts that are due to minor problems with the detectors, and giving us a much better idea of what the sky looks like. Okay. I won't spend a lot of time on this slide because I want to get to some of the images, but here's a little bit more detail on the instrument here, which includes that frozen hydrogen cryostat, which should last us until October, the 40-centimeter diameter telescope, and has 4 megapixel arrays that are taking the pictures in those 4 infrared bands. And then the spacecraft supplies communications and power, and I'm not going to make you remember and understand all those acronyms because if you're interested in becoming a spacecraft engineer, you can ask me more about that, but I think for the rest of us, we'll move on. This is a little more detail on the telescope part. So this is the front of this looks like a lot of telescopes where we have a mirror that gathers the light, the main primary mirror, which is, as I say, is about 16 inches in diameter. So light comes in here, reflects off that mirror. There's another mirror here called the secondary mirror, down through a hole, makes its way through a bunch of things to that scan mirror. And that scan mirror then is going in the opposite direction as the satellite. So that's very important that scan mirror is matching the motion of the satellite. Then there's a bunch of more optics, and finally we get to the detectors. And you can see that maybe a little bit here, so better here. So there's the scan mirror right in the middle, a bunch more mirrors, and then down at the bottom are the focal planes or the detectors. Those turn the light that falls on the images that fall on those detectors get converted into electronic signal voltages that are transmitted along these cables to the electronics that are in the spacecraft, where they're stored and then sent to TDRS. Now here are all the pieces on that instrument coming together. Our megapixel arrays again. Here are those detector arrays with their cables. This is a sunshade to keep the sun and earth from bright, warm infrared light from giving us a lot of glare. That's why we're in space and why we're cooling to frozen hydrogen. And here's how the whole thing kind of sits inside of this giant thermos bottle. This is the thermos bottle. The outside of it here is filled with the frozen hydrogen at about minus 440 degrees Fahrenheit. And here you can see them lowering the actual telescope into the cryostat, and there's the cover that we had to eject just before New Year's. And there it is all put together. And so you can get an idea of how big it is. It looks a little bit like R2-D2. It's, we'll have a full-size picture of it out at the open house in about a month, so you can come and get your picture taken with R2-D2. And here again the cover's off so you can see the primary mirror. Okay, and this is the other major part of the satellite, the spacecraft. And again, I don't want to take time to go through all these parts, but those signals, those electronic signals, are coming into what's called the FEB, the Flight Electronics Box. And there's a computer in here, and there's a digital electronics box. I don't have time to go through all this, but this is our antenna, the one that sends the signals to TDRS. So it's a flat antenna that we point at those geosynchronous satellites 4 times a day, and this is our solar array. And maybe it's a little easier to see here in this picture. There's our solar array, provides us with all the power we need and then some. And on the opposite side is the antenna, and of course there's the instrument and the spacecraft. And here it is, pretty close to its final configuration, all kept clean and bagged up. And that's not enough, though. We need a rocket, so we're going on now to Vandenberg Air Force Base in coastal California. And actually, our deputy project manager, Fengshan Liu, is sitting in the second row here, basically took over at this point and made sure that we didn't do anything stupid. So it's a pretty place, actually. I encourage you to get out there. This is the view driving out from Vandenberg. Here's our processing facility. Here's WISE arriving on a trailer, and there it is being unpacked in the processing facility. And at this point, we're keeping WISE cold all the time. And the way we do that is with a lot of equipment. So we're constantly filling WISE with liquid helium to keep that hydrogen frozen. And here you can see one of the technicians doing exactly that. These people had to work for months, 24/7, making sure that WISE never ran out of liquid helium. And every time you change out a tank of liquid helium, and we're changing out 2 500-liter tanks of liquid helium, there's a chance of getting an ice plug. So there's this constant fear that you're going to develop a dangerous situation. And Feng and many, many others made sure that that never happened. So a real credit to the people that worked out there. Okay, so now we have to get onto our rocket. There's our rocket being assembled with our logo on it. And we have to get WISE up there. So here we've put WISE into a can. This is me and the deputy project scientist, Amy Meinzer, and the PI, Ned Wright, standing in front of the can, putting it on a little truck. This is done at 3 in the morning when it's very, very calm. Take it to the base of the rocket and lift it up, and there it is on the top. Okay, so now all we have to do is launch it. So here we are the night before launch. There's Ned Wright in front of the rocket, gets a solo picture. And at 6:09:33 a.m., this is what WISE was doing. The picture on the right is a little bit later. It's taken with a camera similar to this. It might actually have been this very camera. So that's an infrared view of the WISE launch. Okay. So I was actually right about here at 6:09:33. And then we said, okay, well, let's go outside and see if we can see it. And I was kind of looking over there. And I said, well, I don't see anything. And I think Mark or somebody was saying, no, look over here. And there's this thing that looks like kind of like a Hollywood comet zooming across the sky. I mean, it was cruising. It had this huge tail behind it. So this is my view of a launch. And having seen a couple of launches up close, this was a real surprise to me. I didn't expect it to look like this at all. So it was a lot of fun. Okay. I'm going to start showing you some pictures now from the sky here. So that's kind of what WISE is in terms of hardware, but of course what it's about is mapping the sky. So here's a map of the whole sky. This is our best existing map of the whole sky at the shortest wavelength that we have with WISE, which is 3.5 microns. This was taken by an instrument called Derby on a satellite called COBE, the Cosmic Background Explorer, that actually won the Nobel Prize. And this picture was taken basically in 1989, and with just really just 1 pixel at this wavelength. And because it's just 1 pixel at a wavelength, it actually has pretty crude resolution. I'm going to zoom in on that little green spot now. First, I'm going to show you what it looks like from COBE or Derby. And here you get an idea of how coarse the resolution is. There's the moon for scale. So that's what we have in hand for the whole sky at the shorter wavelengths that WISE observes. If we move out to the longer wavelengths that WISE observes, 12 and 22 microns, this is the view that we have from the IRAS satellite, infrared astronomical survey. It had 62 pixels in total, about 16 per band. And you can see that's doing a little better. We can actually make out there's a star there. It's actually quite a bright star. But remember, WISE has 1 million pixels here, and so it's going to do a lot better. We actually have 4 million pixels, 1 million in each of our 4 bands. So here's the WISE first release image of the sky. This was actually taken with us staring at one place, and this was really the only time that we stared in one place. We wanted to be sure everything was working, and when we saw this image, we said, yes, it's in focus, it's sharp, everything's working. This was a huge relief. I actually saw this just before New Year's and immediately opened the bottle of champagne. It was great. Okay, but now I want to talk about the survey. Okay, so remember the basic idea here. So the satellite's going like this all the time, scan mirrors going like that, and then snapping ahead to catch up. So we've got this sort of motion. Every 11 seconds, we take a snapshot, and we get a little bit of overlap from one frame to the next. And you can see that here. So this little point here is that one. There's a little bit of overlap from this set of images to this set of images. These are in the 4 bands, the 3.4, 4.6, 12, and 22 micron bands, and this is sort of a false color composite of the 4. So every 11 seconds, we get another row of images like this. So this is 33 seconds in the life of WISE. And when you add that up, it's over 7,000 frames a day that are making their way to the ground. And here's where we are as of this morning in terms of covering the sky. So here again is that 2-micron view of the whole sky with the Milky Way going across the middle. And here is the fraction of the sky that WISE has covered, shown in purple. So what we're doing is we're scanning a line. We're always advancing this leading edge here. And right now we've covered a little over 53% of the sky with at least 8 exposures at every position. That doesn't count this blue hole here. And the reason that blue hole is there, this actually is showing all the frames that have made their way successfully through the data processing system at Caltech. And when we got to the center of our galaxy, there were so many stars that with our initial data processing settings, the software got a little confused. It says, I don't know exactly where I'm pointed. It could be here, it could be here. And so it basically said, I can't process this frame. I'm going to go into the next one. So we tweaked the parameters a little bit. We know how to process those images now. We're starting to go back, and all these images are going to be processed fine. But that's why you see that hole there. So in fact, we were advancing across the sky like this, and you can see that we figured it. We started seeing the problem here, and by the time we got over here, we had figured out how to fix it. So that's why it goes all purple again. Okay, so a month after we started that survey, February 17th actually is when we released these. We released selected images, and because WISE is observing everything in the universe, I'm going to show you some examples that step out to larger and larger distances. So I'm going to start with a relatively nearby object in our own solar system. This is comet Siding Spring. It's about 200 million miles away from Earth when this picture is taken, and you can see it has a long tail, which is, of course, the characteristic of comet. But what you're seeing here in red and orange are those 12 and 22 micron infrared views. So much like what you're seeing with the infrared camera here, you're seeing room temperature material glowing. In this case, it's room temperature dust, because this comet is roughly as far from the sun as the Earth is, and so it's at roughly room temperature. And that dust is glowing at room temperature, makes it a very, very prominent object in the infrared. Here's a star for comparison, which is really only showing up brightly in the shorter wavelengths of WISE. Now, comets are actually I could give a whole talk on comets, but obviously don't have time to do that tonight. But they're very interesting sources that are connected with the formation of our own solar system, and by studying them, we get insight into how our solar system forms and evolves. But I'm going to step out now way beyond our solar system to a star-forming region that's halfway across our galaxy, 20,000 light years away now. So this is a very active star-forming region. Down in the middle there, as you can see in this zoom in with the Hubble telescope, there's this little cluster of young hot stars, and there's lots and lots of dust around them. So you can see that the stars have cleared out the dust in their immediate vicinity, but when you get out to here, you start seeing more dust and more dust and more dust. And that's what you're seeing glowing way, way out here. In red, you're seeing our longest wavelength. That's the 22 microns, so that's warm dust again, similar to the comet tail. And in the green here, what you're seeing is our 12 micron band. And what's going on in this band is kind of interesting. It's actually a fluorescent reaction where little carbon ring particles called polycyclic aromatic hydrocarbons, these are soot particles basically that you find in tailpipes, in barbecues, and in star-forming regions. They absorb the visible and ultraviolet light, especially from these hot stars, and then they fluoresce and they re-emit in our 12 micron band. And so we often see these very, very spectacular structures turning up in the band that we color green in these pictures. So the color scheme here is our shorter wavelengths. The 3.4 and 4.6 are showing up as blue, 12 microns showing up as green, and 22 microns as red. I'm now going to, so what we're seeing here is a lot of information about star-forming regions all around our galaxy. This is just one of them. But we can also look beyond our galaxy. Here's the nearest big galaxy beyond our own. This is the Andromeda galaxy, M31. Some of you have probably seen this. You can see it from a reasonably dark sky with your eye. It's about 2.5 million light years away. And the same color scheme here, so red and green are these 12 and 22 micron bands that are showing dust and fluorescing soot particles that are associated with star-forming regions. And you can see now the pattern of star formation is really very interesting, and it's tightly confined in this ring all around. Whereas in the blue light, where you see is sort of ordinary stars that are just kind of doing their own thing, and they're distributed very differently. So we can see patterns of now formation of stars on the scale of a whole galaxy. But of course, WISE looks at everything, so we can go beyond this scale to an even larger scale. Now we're looking at a cluster of galaxies. This is called the Fornax cluster. It's about 60 million light years away. And typically in a cluster of galaxies, what you have is galaxies, big galaxies in the middle that are all just stars like the sun or older than the sun. They're showing up really almost exclusively in our shorter bands, the 3.4, 4.6, which are colored blue here. And the whole center of the cluster is filled with galaxies like that are just not doing much of anything. And I could give another talk on that, and actually I have given another talk on galaxy clusters. But when you get out to the outskirts, you start seeing galaxies start to light up with star formation. And so it looks like what's going on here is as galaxies kind of crash into the center of a galaxy cluster, their star formation is being shut down. Or maybe it's being started up. We actually don't know in detail this, and WISE, by providing images of every nearby galaxy cluster there is, will give us a lot of information about this. Okay, so that's kind of the universe from nearby comets to galaxy clusters. I'm now going to talk about this in a little bit more detail. And for this, I'm going to want to turn on my solar simulator and start heating up some asteroids here. Hopefully this will work. Maybe not. There we go. Okay. So we'll come back to that in a minute. But first, I want to just give you a reminder of the solar system. So this is a top view of the solar system with the sun in the middle, Mercury, Venus, Earth, Mars. All these little white dots here are where most of the asteroids hang out. It's called the main belt of the asteroids. And then we get out to the orbit of Jupiter, quite a bit further out. And that has populations of asteroids that are orbiting with it. Asteroids that are, so there's the main belt. Asteroids that get very close to the Earth are called, not surprisingly, near-Earth objects. The ones that get closer than about 30% of the distance from the Earth to the Sun are near-Earth objects. And they're a particularly interesting population for lots of reasons. One is that they're unstable, and so they're also a very good tracer of the evolution of our solar system. And maybe a little bit more practical, immediate reason they're interesting is that there's a finite chance that one of these will crash into the Earth. In fact, eventually, many near-Earth objects are going to crash into the Earth. And it's generally accepted now that a large asteroid, about 10 kilometers in diameter, is what did in the dinosaurs 65 million years ago. So it's an interesting population to pay attention to, and it's one that WISE has a lot to say about. Here's how WISE sees asteroids. Remember, we're taking a string of images every orbit, and then we come around, shift it a little bit, and look at the same place in the sky again, and then we do it again and again. And we get about 8 or 10 looks at any place on the sky. Well, in that hour and a half that it takes WISE to go all the way around that orbit, the asteroids actually move. And so as we look at the same object from image to image, taken an hour and a half apart, we see these these asteroids moving. And they're red here because they're glowing brightly at our 12 and 22 micron bands. They're room temperature objects because they're roughly as far from the sun as the Earth is, and therefore they're about as warm as the Earth is. And so they glow brightly, just like we here in the audience do, in the infrared bands. So what we're looking for is strings of things that are bright at those 12, particularly at 12 microns. And here's an example that we actually stumbled across accidentally. This is an image that we're planning to release to the public in the next week or two, so I can't show you more than this, unfortunately. It was originally going to be in here, and then I found out today we're going to release it on the JPL website. So watch for a bigger version of this. But I think everyone can see the string of green dots here, and green is that 12 micron emission. So what you're seeing is image after image where that asteroid has moved around. And it's probably rotating, and therefore its brightness is changing a bit from image to image. So we look for these strings of dots. We call those tracklets. And if they're not associated with an asteroid we already know about, we report them to the Minor Planet Center in Cambridge, Massachusetts. And so far, we've reported 44,000 tracklets that don't correspond to asteroids that we already knew about. And here's a little movie that shows, again, the top view of the solar system, the sun not labeled in the middle, Mercury, Venus, Earth, Mars, and Jupiter orbits. And here are the tracklets that we're seeing now. This is all of them, so it includes both the new ones and the ones that we already know about. And if I click on this, you can see that as the survey goes on, initially we had a little trouble getting the software going, and we interrupted the survey a couple times too. But as time goes on, we pick up more and more of these. And so we've now mapped out a good chunk of the main belt, and of course by the end of the mission we'll basically have mapped out not quite all of it, but nearly all of it. You can barely see in here the red dots. Those are the near-Earth objects, and those get special attention. They're posted on a special web page, which I'll show you in a second. But I think I want to go back to my solar simulator should have done its job by now, so I want to go back to the infrared camera and show you why infrared is especially useful for rocks that are orbiting out there. So if we could switch back to the infrared camera for just a minute. Or if that doesn't work, I can show you with the slide here. There we go. Okay, so let me turn off the solar simulator here. And I'm going to put gloves on, not because these are that hot, but because my hands are warm and they would interfere with the infrared view. So I think probably most people can see these rocks here, but maybe it's a little hard to see the one in my right hand, pretty easy to see the one in my left hand, right? And so the reason is that this one is white. It reflects actually a lot more light than this one. And asteroids are like this too. They have a big range in how much light they reflect. And nearly every asteroid that's been found so far has been found using visible reflected sunlight. But of course what WISE is doing is looking in emitted light. So in the same way that you guys are glowing in the infrared, these asteroids, hopefully, should be glowing in the infrared. So let's see if we can prove that actually is the case. There it is. Okay. So let me move that a little bit closer here. Okay. And in fact, you can see that the larger asteroid there, or the larger rock, is glowing even more brightly than the smaller one. So in the infrared, the situation, the bigger one looks brighter, and in fact, it's easier to spot, if anything, whereas in the optical, if you looked at those two things and just measured how bright they were, you might think they were the same size if all you could see was how bright they are. But here in the infrared, we get a much better true measure of what their size is. And that's, if you want to know how much damage a rock is going to do if it hits the Earth, it's sort of helpful to know how big it is. So WISE is collecting information that's really critical to getting size information for hundreds of thousands of asteroids. And that's really important information. So let's go back to the slides here. So we're collecting this infrared emission, and we're getting a much better idea of the size distribution of these rocks that might hit the Earth. So we could go back to the slideshow again. There we go. So we have a special web page that's actually maintained here at JPL by the JPL Near-Earth Object Program. And this one is dedicated to WISE discoveries, and you can see that we have found, there aren't that many of these near-Earth objects, but we've found 34 new ones that weren't known about before. 5 of those are they have orbits that take them extremely close to the Earth. They're called potentially hazardous objects. Here is an example of the orbit of one. It's going to get within less than 10% of the distance of the Earth from the Sun. Actually, at some point in the future, it'll get even closer than this. But you can see in next year, actually just a little under a year from today, it's going to get pretty close. We've found others that get even closer. They get 0.7% of astronomical unit away from the Sun. That's less than 1 million miles, sort of roughly as far away as the Moon is. And these are new asteroids that someday may run into the Earth because their orbits aren't very stable when they're in this part of space. That is, I think, all I have time for in terms of asteroids. So I want to step on now, again, beyond the solar system, tell you a little bit about 2 other topics, one of them being brown dwarfs. Okay, so now we're leaving our solar system behind, and we're going to talk about very, very cool stars, or failed stars. Stars that have less than about 8% of the mass of the Sun don't have enough gravity, enough pressure, enough temperature to sustain the basic fusion reaction which keeps our Sun glowing. So I think most people in the room probably know that the Sun is powered by fusion. Fusion is a wonderful power source. We haven't figured out how to do it in a controlled way on the ground, but we know how to set off fusion bombs. The Sun is constantly converting hundreds of thousands of tons of hydrogen, fusing hydrogen into helium. And in the process, a little bit of the mass, about 0.7% of the mass, actually gets converted into energy. And that 0.7% via the E equal mc squared, famous Einstein equation, comes pouring out of the surface of the Sun and keeps it glowing. And it's been glowing like that for billions of years. But you need more than about 8% of the mass of the Sun to keep that fusion reaction going. If not, the reaction doesn't quite get going. And a star that has less than 8% of the mass of the Sun will radiate, and it will cool off, and it doesn't have any new power source to replenish that energy. And so it will get cooler and cooler, and as it gets cooler, its peak wavelength will shift longer and longer until it becomes too cool to see at all in visible light. But it's still plenty warm enough to show up in infrared light. And so WISE is a major project. One of the 2 key projects for WISE, actually, is to hunt for nearby brown dwarfs that are too cool to see in visible light, but show up in infrared light. And it's not quite as simple as saying most of their light comes out in the infrared here. It actually, because of molecules in the atmospheres of these brown dwarfs, nearly all of the light actually comes out in our 4.6 micron band, which is shaded green here. So I'm going to show you some pictures in a second where we use blue for our shortest band, 3.4, green for 4.6, and actually use, just to confuse you, I'm going to use red for our 12 micron band. And what we're really looking for things that stand out in this green band here. And those are going to be cool brown dwarfs. And we have enough sensitivity to find brown dwarfs that are as cold as minus 100 degrees Fahrenheit. That's pretty cold for a star. But if you have something that's just several times the mass of Jupiter that formed the same way a star is, after 5 billion years or so, that's the kind of temperature where you're going to get to. So there probably are things out there waiting to be found. We just don't know where they are, so we have to look everywhere. So this is the view of the solar neighborhood within 25 light years, all the stars that we know about. But we know of only about 4 or 5 brown dwarfs within this picture. And from other studies, we think there are roughly as many brown dwarfs, maybe more brown dwarfs, maybe a few, maybe not quite as many, but roughly as many brown dwarfs as there are stars. But as I say, only a few of these objects are brown dwarfs. And so WISE is going to find all of these near ones. And so this is the picture of the solar neighborhood, not exactly, because we don't know where they are quite yet, that we expect will happen after WISE is done. All right, so are we actually finding these? Yes, we are. These are some brown dwarfs that we already knew about. They're glowing a fair amount in blue for these. These are some of the hotter ones, but as we get to what's called the T0 type, it starts looking greenish, and T5 is cooler yet, There's the green dot, and T7 is getting really cool. T8 is about as cool as any brown dwarf that we know about. It's about, a couple thousand degrees Fahrenheit, about 1,000 degrees, about 600 degrees centigrade for this guy here. We're finding things that are like this and even cooler that we didn't know about. And here are a couple of them. The green dots in the middle, they're showing brightly in this green 4.6 micron band. And these are, so that 4.6 micron band is called W2 here. And I apologize, this is a negative image, but the thing that looks really black is actually putting out a lot of light in this image. And here's our 3.4 micron band, and you can barely see it there. So things that are much, much brighter here than here are going to look green. Okay? Same situation here. Much, much brighter at 4.6 microns than 3.4, and there's the green dot again. And these happen to be just bright enough that we can look for them in that ground-based near-infrared survey, the 2-micron survey that I mentioned. Just barely see it right there. And you'll notice that that dot actually is not in the center of its circle. And that's because these are pretty nearby objects. And it's been 10 years since that picture was taken. And then 10 years, those nearby brown dwarfs move a little bit. And so that's something, when we come around the sky for a second time, we're going to be looking very carefully for things that move a little bit. And I won't ask you to recite all these molecular features in the spectra, but these are what really prove beyond any doubt that these are, in fact, brown dwarfs. You see that very, very bumpy pattern of lines that, that is characteristic of these cool brown dwarfs. This one is around 1,000 degrees Kelvin, or about 700 centigrade, and this one is as cool as any brown dwarf that we know about. And we've got things that look to be cooler yet that we don't have spectra for yet, but we're working on it. So this project is going very, very well. My last topic, and I thank you for staying with me here. I know I've covered the whole universe basically here, so I know it's a lot to keep track of. I want to leap way, way out now to beyond the galaxy. This is a fairly nearby galaxy called Messier M82, or the Cigar Galaxy. We're seeing a visible light picture of it here and an infrared picture that's taken by the Spitzer Space Telescope on the right. In the visible light picture, you can see some dust, but it doesn't look all that remarkable. But in the infrared, it's clear that something really remarkable is going on. And what's going on is that this galaxy is actually pumping out new stars and heating up dust, and it's fluorescing. Those soot particles are fluorescing. That's what you're seeing in red here. And it's doing that at a rate that is 10 times higher than our galaxy is. And that even though this galaxy is actually about 10 times smaller than our galaxy, it's putting out 10 times more new stars per year than our galaxy. So it's got a rate of star formation that's maybe 100 times higher than our own Milky Way galaxy. So this is really a starburst galaxy. And you can see it's very easy to see that something's going on here by looking in the infrared. So there are galaxies that have even more extreme activity. Those kind of objects, the Cigar Galaxy sorts of objects, are shown in blue here. There's a population called ultraluminous galaxies, and rather than pumping out stars 10 times faster than the Milky Way, they might be doing it 100 times or even 1,000 times faster than the Milky Way. And they're very rare today, but if we go back in time, 8 billion years ago, it looks like they were much, much more common. Now, WISE was designed to have the sensitivity to find objects like this that are 10 billion light years away. And when we think that they were extremely common out here. And so we're going to find them all over the sky and see just how extreme this galaxy formation process can be. That project is a little bit harder to do, and so I can't show you any spectacular results quite yet, but stay tuned. Okay. I want to close with a few more images. We started on March 5th, putting out a new image from the WISE survey every week, chosen, to be honest, mostly for its appearance. This one I really like because you're seeing all kinds of different things in. This is taken close to the plane of our Milky Way, and what you're seeing, and you can get all these pictures, by the way, on our website, shown down at the bottom. You can get them in very high resolution, print them out, make posters, sell them, whatever you want to do. And you're seeing this fluorescing soot particle emission and the warm dust around the star forming region over here. But then here you're seeing this blue glow and this interesting little galaxy here. These are two galaxies that are about 10 million light years away behind our own Milky Way galaxy. And if you looked in visible light, you would not see either of these at all. So you have to go to infrared to see through the dust, like seeing through that plastic bag, to see these things that are hidden by the dust in our own Milky Way. This one to me, I thought looked like moths fleeing a giant stag beetle, but the people who wrote the caption said, no, don't say that. But that's what I like to think of. So here's another one. This is another star-forming region. Again, you're seeing the warm dust glowing and the fluorescing soot particles. Another one. This one we should have released on Valentine's Day, but it didn't come out until March 16th. Again, all of these are available at our website, and some of them, this one in particular, is also available at the JPL/WISE website. And this one is kind of an interesting one. It was taken before we actually started the survey. We hadn't quite matched the rates precisely, but it was a fun one anyway, because you're seeing a whole bunch of things. You're actually seeing a trail from a satellite that's orbiting the Earth at a higher altitude than WISE. You're seeing another comet, Comet Garad, and you're seeing sort of a mini galaxy called Messier 3. It's a globular cluster. There are about 10 million stars here, and these are glowing mostly in the shorter bands in WISE. And here you're seeing the dust glowing in the longer wavelengths in WISE. And in fact, the satellites also glow mostly in the longer wavelengths. And here's one. This again, actually, right, this one's only on the on this site, but I think I've got another one that's on the JPL site. But anyway, you should go to our website, because every week we put up another one, and JPL says, well, we can't have WISE dominate the JPL webpage every day, so we're only going to do one every few weeks. But they're all pretty. Right. This is actually kind of a fun one. This is a galaxy, again, about 10 million light years away beyond our own, or at least we thought it was a galaxy, but I finally realized, no. This is actually the alien from Star Trek in the Day of the Dove episode. Those of you who are serious Trekkies will remember that alien that thrived on violence and was like making Klingons and the Enterprise crew fight with swords. Well, finally, Kang and Kirk realized what was going on. They declared a truce, started telling jokes, and the alien left in a huff, and we spotted it now finally. And this is the one I think that's coming out tomorrow. So another one of these spectacularly beautiful star-forming regions. Okay, I want to just close by pointing out that by mapping the whole sky, by pointing everywhere, we've got information that anyone who's interested in what their object looks like in the infrared can go and look it up. And we're providing that information with hundreds to hundreds of thousands of times better sensitivity than has been available before. So these all-sky surveys are extremely useful for all kinds of projects that we haven't even thought of. And to prove that, here's the number of papers that's been written since the IRAS satellite launched in 1983. And there were a couple hundred the first year, and pretty quickly you got up to about 400, and you stayed there for 20 years. And then about a little more than 10 years ago, actually about 10 years ago, the 2MASS survey was completed, and you can see the same pattern. At first 100, 200 papers, and now we're ramping up to 400 papers. And so we like to say that the legacy of all-sky surveys endures for decades. Okay, so just to summarize here, WISE is going to measure hundreds of thousands of asteroids, get much better size estimates for hundreds of thousands of asteroids in the solar system. We're going to find hundreds of stars in the solar neighborhood that we don't yet know about, including perhaps one that's closer than any star that we now know about. If there's many brown dwarfs as ordinary stars, there's an even chance that one of them is closer than any star we know about, and that would certainly be interesting. It'd probably be the place that JPL wants to send a probe to after we're tired of going to the planets. And we're going to study star-forming regions both in the Milky Way and in galaxies out to 10 billion light years across the universe. But overall, we're going to also do things for people that we haven't yet thought of. As I said, we're going to provide a legacy that endures for decades in enabling studies of objects that we haven't yet even discovered. So thanks for your attention. And I guess we those of you who aren't too tired and want to ask a few questions, I can stay for a few questions. And I've been asked if you can come up to the mic. Right?
Why did you choose, or I don't know if you chose it, but why did you come up with the different microns for the detectors, those different values?
Why those particular wavelength choices?
Yeah.
So the two shorter bands, the 3.4 and 4.6, were designed to really highlight those features on those cool brown dwarfs. So we knew from studies with Spitzer and atmospheric models and other brown dwarf observations that they were very, very bright at 4.5 microns. And we adjusted the filter to really peak up on those. And then we wanted something that showed as little light as possible, and that's set the boundaries of the shorter wavelength filter, the 3.4 micron filter. And so we're looking for things that have an extremely high contrast ratio between those two filters. That's the shorter filters. The longest filter was basically as long as we could get without inventing new technologies. So we wanted to stick to megapixel technology, and that basically got us out to about 25 microns or so. And we had a few hiccups getting the materials to transmit. I didn't say this when I was describing how WISE works, but we divide up the light at the end by transmitting it through filters so that we can get images simultaneously at 3.4, 4.6, 12, and 22 microns. And so we have to actually start transmitting light at that point, and we're more like 22 microns than 24 microns, which is what we originally hoped to get. So that's really what drives the long wavelength, and that's to capture the warm dust and these ultraluminous galaxies that show up brightly in that band. The third, or the final band, which is at 12 microns, is basically designed to span the gap. There's a large gap between 4.6 and 24, and we realized just making that one as sensitive as possible and capturing this fluorescent soot would provide a lot of interest, but it didn't have as strong a driver.
Thank you. Would WISE be useful in detecting the supermassive black hole in the center of the Milky Way, or?
Not the best way to observe that. So black holes, of course, don't directly emit much light unless they're very, very tiny. You see light from things that are falling into them, and because the energies get very, very intense, the temperatures get extreme into the millions of degrees, and so actually it's the shortest wavelengths, the highest energy X-rays and gamma rays that are most useful for studying black holes. But what we can see for bigger black holes is if there's a lot of material falling in, there's typically going to be some dust, and often the ultraviolet and visible light will get obscured by that dust emitted by material falling into a black hole, and you'll see it showing up in the infrared again. And so it actually turns out that supermassive black holes in other galaxies do show up as very red objects, and one of my colleagues has a whole series of papers on just that. So it will be useful for studying statistics of those, but not for studying the black holes in detail.
Can you get any useful science after the coolant evaporates? Can you get better return on investment?
Yeah, we wanted WISE to cover the sky twice. Back in 1998, that's what it was going to do. And one of the cost-saving measures that we made in 2001 was to say, okay, once is pretty good. We only have to do it once. But we hoped that we would have enough cryogen to go around it twice. And one of the reasons is that in the 6 months that it takes to go around the sky, these brown dwarfs will move noticeably. And so if you come back and look at them again 6 months later, you'll be able to tell which are the nearest ones. And so if you could even just do those shorter two filters, the 3.4 and 4.6 micron filters, without the coolant, then you could see if they had moved all across the sky. And we've just gone back to NASA 2 weeks ago, April 7th, last week, and asked for additional funding to let us run without cryogen for a few more months to get all the way around the sky a second time. We estimate that WISE is going to get up to about liquid nitrogen temperature. Once the frozen hydrogen is gone, that's a roaring minus 400 degrees. Actually, it's more than minus 350, actually Thank you. No, it's below minus 300, but I don't remember. It may be minus 350. Anyway, it's warm for our longest wavelengths, but it probably is cool enough for our shortest wavelengths to go. So we hope to do exactly that. We won't know for sure until October, November when the coolant runs out. But we're trying to line up everything to be able to do that.
I have a two-part question. I was going to ask you about extending the cryostat for a period beyond 10 months. And secondly of all, aside from capturing the M31 and M32 and M110 galaxies, is there any way that WISE can possibly capture the entire local group of galaxies and in utilizing the 4 infrared instruments, that is?
I didn't quite understand the last part. Realizing the 4 what?
The 4 infrareds that are aboard the WISE.
The 4 infrared bands. Mm-hmm. Right. Okay. So extending the cryostat lifetime, I think I just answered that.
I think you just answered that.
Okay. So in terms of mapping other galaxies besides the Andromeda Nebula M31 and M32, the little satellite that's above it, and M110, the one that's below it, yes, we're getting everything. That's just what we thought made a nice mosaic picture to release. But we're covering the whole sky, so we're observing. I like to say we're observing everything in the universe that is further from the sun than the Earth is, and all those galaxies qualify.
Will you be observing the entire local group?
Yes.
Thank you.
Let's see. I think we have a few questions that came in on the web. If there are not more here. So let me just take these in order here. How would a black hole or other modern physics phenomenon show up with WISE? And probably that person asked that before I answered. I think it was your second question. But basically the supermassive black holes, as matter falls into them, they put out a lot of high energy radiation, ultraviolet radiation that tends to get absorbed by dust that's also falling in or orbiting the center of a galaxy, and then you get this dust heating up and glowing in the infrared, or the subparticles fluorescing. And so actually one of the signatures of a black hole as opposed to a star forming region is because you have so many more high energy photons, X-rays and gamma rays coming out. They actually destroy the subparticles. And so the real signature of a black hole, a giant black hole at the center of a galaxy, is that you don't see so much of that fluorescent emission. You just see more of the warm dust emission. Okay, I hope I answered that one. How will the information gathered by WISE be used other than for mapping and tracking purposes? Well, okay, so we of course have some specific science objectives. One of them is, I've talked about 3 of them here. We want to measure size distributions for asteroids. I kind of skipped over this. We've actually discovered 7 new comets with WISE. So we're learning a lot about the makeup of the solar system, and we expect to know quite a bit more about how the solar system evolves. We're going to fill out the solar neighborhood. We're going to find how cool brown dwarfs can get, and brown dwarfs are they're sort of the failed end of the star formation process, and at the very bottom end of that masses, as you get way less than 8% of the mass of the sun, you're starting to get things that are similar to the masses of the giant planets that we're now finding around other stars. And so they're helping, by finding intermediate objects, it helps fill in our whole understanding of that sort of middle range between planets and stars. And then of course, by identifying these ultraluminous star-bursting, forming galaxies, cataclysmically forming galaxies, we're finding out how an entire galaxy forms, and finding out how the galaxy formation process goes. And those are actually those are 3 of our science objectives. We have about a dozen that we identified in the proposal. I'm not going to make you sit and listen while I recite all those, but as I say, there's probably hundreds that we hadn't thought of. But there's also very specific, less scientific uses. For example, the James Webb Space Telescope has asked for an early delivery of our catalog to use so that they can develop a good guide star catalog for their telescope, which is able to see much fainter objects than WISE, but only point in very limited number of directions. And of course, those big telescopes will be following up on the interesting objects. So if we find a star that's closer than, a brown dwarf that's closer than any star we know about, like 2 light years away instead of 4 light years away, you can bet we'll want to see if there are planets around it, and all kinds of observatories will want to point at it. I'm going to stop answering these questions because it looks like you have did you have a question for me? Why don't you go ahead and ask it?
Can WISE see dark matter?
Ah, wow, that's a good one. Okay, so dark matter, it's called dark matter because it's really hard to see. And in fact, it really doesn't interact with light very much. And it doesn't matter that it's visible or infrared or ultraviolet or X-ray or radio. There's very, very little influence of dark matter on any of those wavelengths of light. So the short answer is no. And I can talk to you more about it afterwards, but there's a couple more questions here that I want to just try and answer. So with WISE, do we still need Hubble? That's an interesting one, and the answer is yes, for 2 reasons. And you could ask the same question about almost any other telescope or observatory. But the 2 reasons are, one is that WISE is an infrared telescope, and Hubble is really an optical telescope. It goes out into the shorter infrared wavelengths, like the 2-micron all-sky survey does, but it doesn't reach out as far as the 3.4-micron band that WISE does. And so they're complementary in that way, but they're complementary in a much more fundamental way, and that is, well, equally fundamental way, I shouldn't say much more fundamental, and that is that Hubble is designed to take very, very high magnification images, very, very deep exposures, and so it stares at one spot in the sky. Typically, the shortest exposure that Hubble will make is at half an hour or so. Occasionally, it might go as short as 10 minutes. The longest exposure that we make at any point in the sky is about a minute. So we don't really want to focus on any one part of the sky at all. We just want to do it all and find the interesting things that are then worth spending hours and days, and in some cases even weeks, that these more powerful but pointed telescopes can do. So that's the important difference between Hubble and Spitzer and James Webb Telescope and WISE. And if there aren't any other questions, this last one is an interesting one. So what is the most important discovery made by WISE? I look forward to answering that question a little bit after the WISE survey is done, because we're only halfway through covering the sky. Things are going great, but so far, what is the most important discovery made by WISE? I would have to say, to me, the most surprising discovery that has come in is that there are sizable asteroids out there that we didn't really expect to find. Now, we're still gathering statistics, but there are asteroids that have orbits that are very, very different than most of the asteroids that we know about. And that's probably true because we spend a lot of time looking at all parts of the sky, and most of the surveys that have been done so far concentrate on the plane of our solar system. And we also are doing an infrared survey, so we're sensitive to objects like that dark rock there that might have missed detection so far. So there are objects with weird orbits that are in our solar system, and there are objects that are pretty dark, and there are objects that are coming pretty close to the Earth. And so I'd have to say that WISE is very likely to change our understanding of the makeup of our own solar system. But that's just the most important discovery so far. So with that, thanks again.